Today we are going to solve the problem 5.6 of Griffith third edition Introduction to Quantum Mechanics. I have already solved this using a lengthy mathematical step. Here I am going to use the simplified mathematical version. So imagine two non-interacting particles each of mass m in the infinite square well. If one is in the state of psi sub n, equation 2.28, and the other in state of psi L, where L is not equal to n. Calculate the expectation value of x minus 1 whole square, assuming that they are distinguishable particle, they are identical boson, and see they are identical fermion. Now we will solve one by one. Uh, Before going into the detail, please refer my earlier lecture on solution to Griffith problem 2.4. From 2.4, we have seen the expectation value of x is equal to a over 2. That is at the middle of the box. And the expectation value of x squared is equal to a squared 1 over 3 minus 1 over 2 n pi whole squared. This is the value we got from the problem 2.4. So I don't want to repeat it here. Kindly refer that lecture. So first we will take the distinguishable particle. That is A, distinguishable particle. That is here in the left hand side. It is the square of the expectation value of distance between the particle 1 and particle 2. That is the meaning of this. That is the distance between two particles is x1 minus x2, and it is, we are going to square it, and you see this subscript t represents these particles are distinguishable, which can be written as a minus b whole squared is a squared b squared minus 2ab. So here you can use this can be written as expectation value of x squared of the particle A plus the expectation value of the particle P, that is the expectation value of square of the x squared of the particle P, and minus 2 expectation value of particle A multiplied by the expectation value of particle P. Now you substitute it. See, expectation value of A squared is equal to A squared 1 over m minus 1 over 2 n pi squared plus this one, the expectation value of P. Uh, as given in the problem, A and P are at a different state. That is, L is not equal to M. So, N is not equal to M. So, we have written for particle 2, it is A squared multiplied by 1 over 3 minus 1 over 2 M pi square. Then expectation value of H for particle A is A by 2, for particle P also A by 2. So we will try to simplify this. We have seen that the difference in the square of the expectation value of x minus x2 is equal to a square 1 over 3, this expression. Here you take last term. In the numerator you have a square, and in the denominator these two will get cancelled. So you will get uh, a square over 2. Here you add, here now we have a square in all the terms, so you take a square outside. Here you have 1 over 3, here 1 over 3, which will become 2 over 3 minus 1 over 2 pi square n square. Here it is 1 minus 1 over 2 pi square m square, and this is 1 over 2 because I have taken a square outside. So now if you take the common factor, uh, 2 over 3 minus 1 over 2 is equal to 1 over 6. And here you can see that 2 pi squared and 2 pi squared is common. 1 over 2 pi squared, 1 over 2 pi squared. So I am taking 1 over 2 pi squared as a common parameter. Then this will become 1 over n squared plus 1 over m squared. This is the square of the expectation value of square of the distance between particle 1 and particle 2 when they are distinguishable. Then for boson, identical boson, you cannot distinguish this. So as given in the equation 5.25, equation 5.25 of Griffith, it is equal to expectation value of the square of the difference in distance between particle 1 and particle 2. Here sub plus or minus indicate plus means a symmetrical one. For boson it is symmetrical. For fermion it is antisymmetric, that is minus. So the common expression is expectation square of the expectation value of x for the particle A and for particle B minus 2 times the expectation value of particle A plus the expectation value of particle B. You can see the yellow color. This we have seen this entire term, three term is nothing but the expectation value, the square of the difference between the particle 1 and 2, expectation value of the square of the distance between particle 1 and 2, this three parameter, that is by t. We can represent this as expectation value of x1 minus x2 whole square, and this is for distinguishable particle, and at that time I am keeping it as it is minus or plus 2 times the interaction between the expectation value of x ab, interactive term or interference term, modulus square. Remember that. This is upper sign is for symmetric particle, and lower sign plus is for antisymmetric particle. Now, based, with this introduction, we will move further. Now we got this relation, and already we have calculated this one. That is uh, difference in the distance between particle 1 and 2 whole square, the expectation value for distinguishable particle minus or plus 2 times the modulus square of the expectation value of A, B. So interactive term this will be. So now we have to calculate this one. We have to calculate. So the expectation value of x mn is equal to, you know, the wave function for infinite square well potential, which is equal to a square root of 2 over a sine kx, where k is equal to n by a. We know it. So I am writing that as uh, when you take the square of this, this will become 2 over a x, because by definition the expectation value of x is equal to x sine m pi over ax sine n pi over ax dx. So this can be written as uh, 1 over 2, but 1 over 2, when you are taking 1 over 2, this 2 will get cancelled with this 2. So you will get simply 1 over a, and this x, that is sine a into sine p is equal to sine a into sine p is equal to cos a minus p, cos a minus p minus cos a plus p. So using that formula, this is equal to 1 over 2 cos a minus p minus, of course, 1 over 2 is a common, cos a plus p. So this 2 will get cancelled with this 2. You will get 1 over a. Then you have x here. This can be written as cos m minus n pi over a multiplied by x minus cos m plus n pi over a x. Uh, if you integrate this, that is integral of x cos kx dx is equal to, if you use the integration by parts, you will get the final result as x over k. I have explained this in so many lectures. X over k sin kx. Of course, you have to apply the limit 0 to a. Then 1 over k squared cos kx. Here also you have to apply the limit 0 to a. So first term, if it is 0, lower limit x will be 0. What about x is equal to a? Here if you put x is equal to a, this will become m minus n. First integration m minus n pi. Whether it is odd pi or even pi, that is m minus n pi or m plus n pi, this will be always 0. So you can ignore this term. You can take only the second term and you have to apply the limit. We will do it now. Now we got this integration. We got to solve this. Of course, we have seen that I integral for this type of format is I is equal to 1 over k squared cos kx. You have to apply the limit 0 to a. I have already explained the first term, sin term will get cancelled. So only the second term we are getting, which is equal to 1 over k squared cos kx. We have to apply 0 to a. If you apply the same for the first term, then here you have to remember that this value of cos depends upon whether m minus n is odd or even. So if it is even, then it is plus 1. If it is odd, then it is minus 1. That you have to keep it in your mind. Then what is k squared? This is k. For first term, this is k. So if you square it, you will get m minus n n squared pi squared over a squared. A squared will come upside. And when you apply the upper limit for cos kx, then this will be minus 1 power m plus n. Of course, for lower limit, it is minus 1. So minus 1 lower limit. Similarly, for the second one, k is this one. If you apply the upper limit here, when x is equal to a will get cancelled. This will become m plus n whole squared pi squared. This one over a squared. Of course, you will get minus 1 whole power m plus n. If it is add m plus n is add, then it is plus 1. If it is even, it is minus 1. So for lower limit, this is minus 1. If you take common as, you can take a over here, you have pi squared, here pi squared, here pi squared. You can take that as a common a over pi squared, and this also you can take this numerator. In both the numerator you have minus 1 power m plus n minus 1. So here as well as here. I have already taken a squared outside. So a squared will become, a squared will get cancelled with this a. That is 1 over a. I am taking a squared outside. Then this will become a over pi squared minus 1 whole power m plus n minus 1. Then you take this as common, m minus n whole squared multiplied by m plus n whole squared. Then this numerator will become m plus n whole squared minus m minus n whole squared. Then we will further simplify it. So we got this expression. Now you take the numerator. Numerator will be in the form of a plus b whole squared minus a minus b whole squared is equal to 4ab. This is a well-known result. So this numerator will become 4mn. And here I'm going to uh, separate this m minus n here, another m minus n, and m plus n multiplied by m plus n. Here, what is this value? This is m squared minus n squared. Similarly, this two term is m squared minus n squared. So the denominator will become m squared minus n squared whole square. Now we can find the result, final result. Uh, if m and n have opposite parity, that is, any one of it is one is add and one is even, then summation is add. So when it is add, you will get minus 1, minus 1. So which will become minus 2. Then this 4 will become 8. So minus 8 mn, and we are taking a over pi squared as it is, and here m squared minus n squared whole square. If fourth have same parity, that is m and n is add, or m and n is even, both are add, both are even, then the sum will be always add. So then it will become plus 1 minus 1, which is equal to 0. So we got this interactive term as if m and n have opposite parity, we got this. If it is same parity, we will get 0. With this, we will continue further. So we got this expression. As I said, the when particle are distinguishable, you will get this one. For distinguishable particle, we have seen is 1 over 6 minus 1 over 2 pi squared multiplied by 1 over n squared minus 1 over m squared. And the interactive term, we got it like minus 2 times this expectation value of AP modular squared is equal to A by pi squared minus 8mn. Just now we have seen m squared minus n squared whole square. So if you bring these two inside, this will be 8 squared is 64 plus 64, and if you multiply 64, you will get 128. So you got this term. Here I like to highlight one important point. When identical particle are far away, this is the particle A and this is particle B, then you cannot have any interaction. So that interaction term will become 0. Uh, you can distinguish because one particle and the other particle is far away. Similarly, for identical boson. So for identical fermion, as I said, you have to take upper sign minus. So you will get minus. So I have mentioned that the distance between x1, x2 whole squared for boson is equal to this one. So I have used negative sign. And for identical fermion, that minus negative sign will become plus. So when the particle become boson become uh, closer and closer, it will be you will get an attractive force. That is a total distance for boson is less than that of the distinguishable particle. So there will be overlapping interference. So they is equal to they have attractive force and comes closer. Whereas for identical fermion, this distance you are adding, so it will move away. That is repulsive force. So you know very well that fermion cannot have two fermion cannot have same state. So it will go far away. That is very interesting thing. Thank you very much for watching my video and supporting me continuously. Thank you very much.